Nothing and everything. Two words that seem to stand at opposite ends of existence, yet together they shape the very fabric of our universe and our understanding of it. Imagine a void so complete it terrifies the mind, a blank slate where even the idea of something feels impossible. Now picture the opposite, a cosmos so vast, so teeming with stars, galaxies and mysteries that it stretches beyond the limits of imagination. This is the dance of nothing and everything, a paradox that has haunted philosophers, sparked scientific revolutions, and fueled humanity's greatest discoveries. From Aristotle's fear of the void to the quantum hum of empty space, from a single supernova shattering the heavens to the dark energy racing our universe toward an unknown fate, this is the story of how we've chased the shadows of absence and the brilliance of infinity. So, take a deep breath, step into the silence before the symphony begins. And let's explore the hidden power of nothing and the boundless wonder of everything. Imagine a world where the very idea of nothing was terrifying. A world where the absence of something, anything, was so unthinkable that it was banished from thought itself. That's where our story begins, thousands of years ago, in the bustling marketplaces and sunlit hills of ancient Greece. It was a time when philosophers were the rock stars of their day, their ideas shaping how people saw the world. And one man, a thinker named Aristotle, stood above them all. His mind was a furnace, forging ideas that would burn through history for over 1,000 years. Aristotle looked at the world around him, the buzzing bees, the rustling leaves, the flowing rivers, and he saw order. Everything had a place, a purpose. But when he turned his gaze to the idea of nothingness, of empty space, he shuddered. To him, nothing was chaos, a void that nature itself despised. Nature abhors a vacuum, he declared, and those words became a law, etched into the minds of generations. Imagine it. The universe in Aristotle's eyes was like a tightly packed room, every corner filled with matter, with life, with something. The idea of an empty space, a true void, was as unnatural as a fish walking on land. And so, for centuries, people believed him. Why wouldn't they? When you look around, there's always something there, air, dust, light. Nothingness seemed impossible, a ghost that vanished the moment you tried to grasp it. But Aristotle's words weren't just philosophy. They were a challenge that would take over 1,000 years to answer. Let's fast forward to a time when the world was waking up, when curiosity was starting to chip away at old certainties. It's the 17th century, and Europe is alive with new ideas. Sailors are charting unknown seas, artists are painting masterpieces, and scientists, though they didn't call themselves that yet, are beginning to question the world in ways Aristotle never imagined. I want you to picture a simple object, something you've probably used without a second thought, a drinking straw. It's not much to look at, just a hollow tube, but it holds a secret that would shake the foundations of Aristotle's world. If you sucked the air out of a straw, the liquid would rush up to fill the space. And if you blocked one end and sucked hard, the straw would crumple, as if the universe itself was fighting to keep that empty space from existing. It's a simple thing, but it's a clue that nature doesn't like emptiness, just as Aristotle said. Or does it? That question, that tiny moment of doubt, is where our story takes a turn. Let's travel to Italy, to the year 1643, where a man named Evangelista Torricelli is about to do something extraordinary. Torricelli was a Jesuit, a scholar with a sharp mind and a restless spirit. He'd studied under the great Galileo, a man who dared to challenge the heavens themselves. But Torricelli wasn't looking at the stars, he was looking at something much closer to home, the air we breathe. He'd noticed something odd. When you try to create a vacuum to remove all the air from a space, nature seems to push back. Think about that straw again. When you suck the air out, the liquid rises as if the air outside is pressing down, refusing to let the void exist. Torricelli wondered, what if the air itself has weight? What if it's pressing on us all the time, filling every gap, every corner, just as Aristotle believed? But unlike Aristotle, Torricelli wasn't content with ideas alone. He wanted proof. So he devised an experiment, one so simple yet so brilliant that it would change the way we see the world. Picture this. Torricelli takes a long glass tube, seals one end and fills it with mercury, a heavy, silvery liquid. He clamps his finger over the open end, flips the tube upside down and places it in a dish of mercury. Then he lets go. The mercury starts to drain out, but it doesn't empty completely. It stops, leaving a space at the top of the tube, a space with no air, no dust, no anything. For the first time in history, a human had created a true vacuum, a tiny pocket of nothingness right here on Earth. Torricelli's heart racing as he stared at that empty space. He'd done the impossible. He defied Aristotle, defied 1,000 years of belief. But what was this nothingness he'd created? Was it really empty? And why did the mercury stop falling? Torricelli realized something profound. The air outside was pushing down on the mercury in the dish, balancing the weight of the liquid in the tube. The air wasn't just there, it had weight, pressure, a presence. He wrote, "We live at the bottom of an ocean of air." Think about that for a moment. We're not just surrounded by air, we're submerged in it, swimming through an invisible sea that presses on us every second of every day. Torricelli's experiment was a spark, a flare in the darkness of old ideas. But it was just the beginning. Across the Alps in France, another mind was picking up the thread. His name was Blaise Pascal, a man who was part philosopher, part scientist, and all genius. Pascal was young, barely in his 20s, but his mind was like a storm, churning with ideas. He'd heard about Torricelli's work, and he was hooked. If air has weight, he thought, then it must behave differently in different places. Imagine you're climbing a mountain. The higher you go, the thinner the air feels, the harder it is to breathe. Pascal wondered, could we measure that change? Could we prove that the air thins out as you rise, that it fades into the vast emptiness of space? So he devised a plan, one that would take him, or rather his instruments, higher than anyone had gone before. In 1648, Pascal stood at the base of a great tower in Paris, a towering structure that loomed over the city. He didn't climb it himself, his health was frail. Instead, he sent his brother-in-law, a man named Perrier, with a mercury tube like Torricelli's. Perrier climbed step by step, carrying the fragile glass tube, his breath growing shorter as he ascended. At the top, he set up the experiment and watched the mercury. And there it was. The level was lower than it had been at the bottom. The higher you go, the less air there is to push down. Pascal's heart must have leaped when he heard the news. This wasn't just about air, it was about the universe. If the air thins out as you rise, then beyond the Earth's atmosphere, there must be a vast, silent void, a vacuum stretching out forever. Aristotle was wrong. Nature didn't abhor a vacuum, it embraced it. The emptiness of space wasn't a flaw, it was the default, the canvas on which the stars were painted. But Pascal's discovery wasn't just a triumph, it was a doorway. He'd shown that we could create and study nothingness right here on Earth. Scientists began to wonder, what's in this vacuum? What are its secrets? They started building better tools, better ways to suck the air out of chambers and peer into the void. And what they found was astonishing. In a vacuum, a bell rings, but you can't hear it. Sound needs air to travel. But light? Light sails through the emptiness, bright and unhindered. This was a puzzle. If the vacuum was truly empty, how could light move through it? Scientists began to whisper about an invisible substance, something they called the luminiferous ether, a mysterious medium that carried light across the void. It was a tempting idea, a way to fill the emptiness with something familiar. After all, if nature abhors a vacuum, maybe the universe has found a way to cheat, to hide something in the nothingness. But was this ether real? Or was it just a ghost, a shadow of Aristotle's old fears? The answer would come from a new generation of scientists, men and women who weren't afraid to challenge the invisible. They'd build machines of incredible precision, tools that could measure the unmeasurable. And what they'd find would turn the idea of nothingness upside down. The vacuum, it turns out, wasn't what it seemed. It wasn't empty at all. It was alive, buzzing with secrets that would lead us to the very heart of the universe. But that's a story for another chapter. For now, let's pause here, with Torricelli's Mercury Tube and Pascal's Tower, with the first glimpses of a void that's not a void. Because the question remains, if we strip everything away, what's left? Is it really nothing, or is it something we can't yet see? Picture yourself lying on a grassy hill, the night sky above you a glittering tapestry of stars. It's a sight that stirred human hearts for millennia, sparking questions that feel as vast as the cosmos itself. What are those twinkling lights? How far do they stretch? Is there an end to the sky, a boundary where the universe stops? These are the questions that have driven explorers, poets and scientists to gaze upward, searching for the shape of everything. In our last chapter we saw how brave minds like Torricelli and Pascal cracked open the idea of nothingness, proving that the vacuum, the void, was real. Now we're turning to the opposite extreme, the infinite, the boundless, the everything. This is the story of how we began to map the cosmos, how we traded a cozy, star-crusted shell for a universe so vast it defies imagination. And it all starts with a single dazzling light that changed everything. It's November 1572 and the world is a very different place. In Europe, kings and queens rule, alchemists chase the secrets of gold, and the night sky is thought to be a fixed, unchanging dome, a shell of stars wrapped around the earth like a protective blanket. People believed the heavens were perfect, eternal, every star nailed in place by the hand of creation. To them, the universe was small, knowable, centered on our little planet. But then, something impossible happened. A new star appeared, blazing brighter than Venus, so brilliant it could be seen in the daylight. You can imagine the gasps, the whispers, the fear and wonder that rippled through towns and villages. Was it a sign from the heavens? A warning? A miracle? This wasn't just a light. It was a crack in the perfect order of the cosmos. We now know it was a supernova, an exploding star, but to the people of 1572 it was a mystery that demanded answers. In a quiet corner of England in the town of Wallingford, a young man named Thomas Digges was staring at that new star with a mix of awe and curiosity. Digges was no ordinary dreamer. He was an astronomer, a mathematician, a man who loved to puzzle out the secrets of the sky. His mentor, a scholar named John Dee, had taught him to question everything, to look beyond the obvious. As Digges watched the supernova, called the phenomenon by those who saw it, he noticed something strange. It didn't move like the planets which wandered across the sky. It stayed fixed, like the stars. But it wasn't there before, and over months it began to fade. Digges and Dee wondered, could this be a star that moved closer and then drifted away? Their idea was wrong, but it was a spark, a daring thought that lit a fire in Digges's mind. What if the stars weren't fixed in a shell at all? What if the sky wasn't a dome, but something far grander? For years, Digges wrestled with this idea. He studied the works of Nicholas Copernicus, the revolutionary who'd argued that the Earth orbited the Sun, not the other way around. Copernicus had placed the Sun at the center of the universe, with the stars forming a distant fixed shell. It was a bold vision, but Digges felt it didn't go far enough. What if the stars weren't confined to a shell? What if they stretched out forever, scattered through an endless void? In 1576, Digges published his idea not as a grand treatise, but as a simple diagram tucked into an English translation of Copernicus's work. His diagram was a quiet rebellion, a vision of a universe without walls, without limits. For the first time, someone had dared to imagine that the cosmos might be infinite, that the stars might go on forever. It was a breathtaking leap, one that made the Earth feel both tiny and wondrously free. But Digges's idea wasn't just beautiful, it was troubling. If the universe was infinite, filled with countless stars, then why was the night sky dark? Think about it. In an infinite universe, every direction you look should eventually hit a star, a blazing point of light. The sky should be as bright as the sun day and night. This puzzle, later called Olbers' paradox, was a thorn in the side of Digges's vision. Digges didn't have an answer, but his question was a gift, a challenge that would echo through the centuries, pushing others to probe deeper into the cosmos. His infinite universe was a dream, but it was a dream that needed proof, a way to measure the unmeasurable. And that proof would come not from books or diagrams, but from the hands of two siblings who built windows to the stars. Let's leap forward to the late 18th century, to a small house in Bath, England. The world is changing fast. The Industrial Revolution is stirring, steam engines are puffing to life, and science is becoming a force of its own. In this house live William Herschel and his sister Caroline, two people who would redefine our place in the universe. William was a musician by trade, a composer who played the oboe and wrote symphonies. But his true passion was the stars. By night he'd peer through homemade telescopes, his eyes hungry for the secrets of the sky. Caroline, his devoted sister, was his partner in this quest. She wasn't just an assistant, she was a scientist in her own right, with a sharp mind and a steady hand. Together they turned their home into a workshop, a place where music and starlight mingled. William had a problem, though. The telescopes of his day were clumsy, their glass lenses dim and blurry. He'd read about a design by Isaac Newton, one that used mirrors instead of lenses to capture starlight. Mirrors could be polished to perfection, gathering more light, revealing fainter stars. So William and Caroline set to work, smelting metals, pouring molten alloys and grinding mirrors by hand. It was grueling work, sometimes dangerous. Molten metal once spilled, cracking the stone floor of their workshop. But their persistence paid off. Their telescopes were marvels, sharper and more powerful than anything before. With them, William and Caroline could see deeper into the cosmos than any human ever had. Night after night, they scanned the heavens, cataloguing stars, sketching patterns, chasing the unknown. One night in 1781, William spotted something odd, a faint, fuzzy object that moved slowly across the sky. It wasn't a star or a comet, it was a planet, the first discovered in human history. He named it Uranus, and overnight he became famous. The King of England made him the royal astronomer, giving him the resources to build even bigger telescopes. But William and Caroline weren't content with one discovery. They wanted to map the entire sky, to draw a picture of everything. In 1785, William published a stunning image, a map of the Milky Way, our galaxy. He saw it as a vast disk of stars, with our sun nestled near the centre. To him, this was the universe, a bounded, knowable whole. He believed he'd seen its edges, the limits of everything. But there was a catch. As William and Caroline peered through their telescopes, they noticed strange cloudy patches in the sky, objects called nebulae. Some were faint smudges, others had intricate shapes like spirals or glowing knots. What were they? Were they clouds of gas within the Milky Way, or something far grander? A few astronomers dared to whisper a radical idea. What if these nebulae were other galaxies, island universes as vast as our own, floating in the infinite void Digges had imagined? The thought was thrilling, but impossible to prove. William's telescopes, for all their power, couldn't measure the distances to these distant objects. He and Caroline could see the cosmos, but they couldn't touch it, couldn't pin down its true scale. The universe was slipping through their fingers, a puzzle half solved. This is where our story pauses with the Herschel's starlit dreams and Digges's infinite vision. The sky was no longer a shell, but a boundless expanse, teeming with stars and mysteries. Yet the question of the dark night sky lingered unanswered, and those nebulae, those ghostly shapes, hinted at a universe far larger than anyone dared believe. The tools to unlock these secrets were still to come, forged by new minds, new machines, and a woman whose quiet brilliance would change everything. But that's a tale for another chapter. For now, let's hold on to this moment, with the stars above and the infinite below. Because the cosmos is whispering a question. If the universe is endless, what lies beyond the Milky Way? And why in all that vastness does the night stay dark? We're standing at a crossroads in our journey, caught between the vastness of the cosmos and the mystery of the void. In our last chapter, we watched as Thomas Digges shattered the shell of stars, imagining an infinite universe, while William and Caroline Herschel mapped the Milky Way with their gleaming telescopes. They gave us a glimpse of everything, a universe stretching far beyond our grasp. But now, let's imagine the empty box. What's inside it? Is it truly empty, or is there something we can't see? Something that fills the vacuum with secrets? This is the story of a chase, a hunt for an invisible substance that scientists believed hid in the emptiness of space. It's a tale of brilliant minds, ingenious machines, and a discovery that turned the idea of nothingness upside down. It begins with a simple question: how does light travel through nothing at all? Let's rewind to the 17th century, where Evangelista Torricelli and Blaise Pascal showed us that a vacuum, an empty space, was possible. They created pockets of nothingness right here on Earth, defying Aristotle's ancient claim that nature abhors a vacuum. Scientists were thrilled. If they could make a vacuum, they could study it, poke at it, see what it was made of. And so they built better tools, glass chambers, pumps that sucked out air, seals that kept the void intact. One experiment stood out, and it's one you can almost picture in your mind. Imagine a bell, small and shiny, hanging inside a glass chamber. In normal air, it rings with a clear, bright chime. But when the air is pumped out, when the chamber becomes a vacuum, something strange happens. The bell still moves, still vibrates, but the sound vanishes. Silence. It's eerie, like the bell is shouting into a void that swallows its voice. This was a revelation. Sound, it turns out, needs air to travel. It's like a wave rippling through water. Without the water, the wave can't move. But then the scientists noticed something else, something that didn't make sense. Light, whether from a candle, a spark, or the sun itself, sailed through the vacuum as if the emptiness wasn't there at all. The bell was silent, but its gleam was as bright as ever. How could this be? If sound needs air, what does light need? This question gnawed at scientists through the 18th and 19th centuries. They knew light acted like a wave, just like sound. Think of ripples on a pond spreading out in smooth, rhythmic patterns. Sound waves travel through air, so light waves, they reasoned, must travel through something too. But what? The vacuum was supposed to be empty, a perfect nothing. Yet light crossed it effortlessly, carrying the glow of stars from billions of miles away. To solve this puzzle, scientists invented an idea, a ghostly substance they called the luminiferous ether. The ether was invisible, weightless, intangible, yet they believed it filled every corner of the universe, even the deepest vacuum. It was the medium that carried light, the unseen ocean through which starlight swam to reach our eyes. It was a comforting idea, a way to make sense of the impossible. After all, if nature abhors a vacuum, maybe the ether was nature's way of filling the void. But the ether wasn't just a guess. It was a challenge. If it existed, it should be detectable, measurable, something you could point to and say, there it is. By the 19th century, science was no longer about philosophy alone. It was about proof, about building machines to test ideas. Albert Michelson, a young American physicist with a knack for precision and a hunger for tough problems, Michelson was a character, intense, ambitious, the kind of person who'd stay up all night tweaking a single screw to get a measurement just right. He'd already made a name for himself by measuring the speed of light with astonishing accuracy, a feat that earned him a ticket to Europe to rub shoulders with the world's best scientists. There in the 1880s he heard about the ether, the mysterious substance everyone was buzzing about. It was the puzzle of the day, and Michelson saw his chance to crack it. The idea was simple but daring. If the ether existed, it should act like a kind of cosmic wind. Picture the Earth moving through space, orbiting the Sun at thousands of miles per hour. If the ether was a fixed medium, like air in a room, the Earth should be ploughing through it, creating a breeze of ether that scientists could measure. Michelson reasoned that light should travel at different speeds depending on whether it was moving with this ether wind or against it. It's like swimming in a river. You go faster downstream than upstream. If he could measure tiny differences in the speed of light, he'd have proof of the ether's existence. But there was a catch. Light is insanely fast, 186,000 miles per second. The Earth's motion through the ether would cause only a minuscule change in that speed, like a whisper in a hurricane. To detect it, Michelson needed a machine of unbelievable precision, something no one had ever built before. So Michelson got to work, sketching designs, crafting instruments, and teaming up with another scientist, Edward Morley, a chemist with a steady hand and a sharp mind. Together they built what would become one of the most famous machines in science, the Michelson-Morley interferometer. It was a marvel, a delicate dance of mirrors and beams set on a block of sandstone floating in a pool of mercury to keep it steady. The idea was to split a beam of light into two paths, send them in different directions, and then bring them back together. If the ether was there, the light beams would travel at slightly different speeds, creating a pattern of light and dark that Michelson could measure. This was his moment, his chance to unveil the ether to the world. In 1887, in a basement in Cleveland, Ohio, Michelson and Morley ran their experiment. They turned their machine, measured again, turned it again, checking every angle, every possibility. They expected to see the telltale pattern, the proof that the ether was real. But what they saw was nothing. No pattern, no difference, no ether wind. Light travelled at the same speed, no matter which way it went. It was a shock, a failure that left them stunned. Michelson, who'd staked his reputation on precision, couldn't believe it. He thought he'd made a mistake, that his machine wasn't sensitive enough. But he was wrong. The experiment was perfect. The ether, the invisible ocean everyone believed in, simply wasn't there. The vacuum, it seemed, was truly empty, a void that light crossed without any help at all. This failure was a turning point, a crack in the foundation of 19th century science. Scientists scrambled to explain it. Some clung to the ether, proposing wild ideas to save it. Others began to wonder if the vacuum was stranger than they'd imagined. The answer came in 1905 from a young clerk in a Swiss patent office, a man named Albert Einstein. Einstein was a dreamer, a thinker who saw the world through equations and imagination. He'd been puzzling over light, space and time, and he had a radical idea. What if light didn't need a medium? What if it was its own kind of wave, a ripple of electric and magnetic fields that could travel through empty space? Einstein's theory of special relativity threw out the ether entirely. Light, he said, was a law unto itself, moving at a constant speed no matter where it was or how fast you were going. The vacuum wasn't filled with an invisible substance, it was a stage, a blank canvas where light danced alone. Michelson and Morley didn't find what they expected, but they trusted their results. Einstein didn't cling to old ideas, he built a new world from scratch. Together, they showed us that the vacuum was emptier than we'd ever dreamed, a place where light needed no crutch to shine. But this discovery wasn't the end, it was a beginning. If the ether was gone, what was the vacuum really like? Was it truly nothing, or was there something else, something even stranger, hiding in the void? Scientists were about to find out thanks to a new kind of physics that would make the impossible real. The vacuum, it turns out, wasn't silent, it was singing, buzzing with a hidden energy that would change everything. But that's a story for our next chapter. For now, let's linger here with the ether's ghost fading away and a new question rising. If the vacuum is empty, what's making it shimmer? We've been chasing the secrets of nothing and everything, from the infinite stars above to the empty void below. In our last chapter, we watched as Albert Michelson and Edwin Morley shattered the myth of the luminiferous ether, proving that light dances through the vacuum without a medium. With Einstein's genius, we learned that the void is emptier than we ever imagined, a silent stage for light's cosmic journey. But what if that emptiness isn't as empty as it seems? What if the vacuum, the nothing we thought we understood, is alive with secrets we're only beginning to uncover? This is the story of a revolution, a leap into a strange new world where the rules of reality bend and twist. It's the tale of the quantum void, where nothingness hums with energy, where particles pop into existence from nowhere. It begins with a simple box, an empty space that holds the key to the universe itself. Let's step into the late 19th century, a time when the world was buzzing with invention. Electricity was lighting up cities, steam engines were roaring, and science was racing forward like never before. The vacuum, that pocket of nothingness Torricelli first created, was no longer just a curiosity. It was a tool, a window into nature's deepest truths. Scientists had learned to make vacuums better and cheaper, sealing them inside glass bulbs and chambers. These vacuums weren't just for experiments, they were changing everyday life. Think of the light bulb, a glowing filament trapped in a vacuum, shining bright because there's no air to burn it out. Or the early X-ray machines which revealed the bones beneath our skin thanks to the vacuum's clarity. But the real revolution wasn't in technology, it was in ideas. Those vacuums so carefully crafted became laboratories for the tiniest building blocks of nature. Without air to muddy the results, scientists could study particles and rays like never before. In 1895, a German physicist named Wilhelm Röntgen discovered X-rays in a vacuum tube, a breakthrough that changed medicine forever. A year later, another scientist, J.J. Thomson, used a vacuum to identify the electron, a speck of negative charge that's part of every atom. And by 1909, Ernest Rutherford was probing the atom's structure, firing particles through vacuums to reveal a nucleus at its heart. Each discovery was a piece of a puzzle, a glimpse of a world smaller than anyone had imagined. This was the dawn of quantum mechanics, a new kind of physics that didn't play by the rules of the everyday world. Quantum mechanics is a strange beast, and to understand it, we need to meet one of its pioneers, Werner Heisenberg. Heisenberg was a young German physicist in the 1920s with a mind that crackled with ideas. He was fascinated by the subatomic world, where particles like electrons behaved in ways that defied common sense. In 1927, he stumbled onto something profound, something that turned our understanding of reality upside down. It's called the uncertainty principle, and it's one of those ideas that sounds simple but shakes the foundations of everything. Imagine you're at a racetrack watching a speeding car zoom past. You decide to take a picture. If you set your camera to a fast shutter speed, you capture a sharp, clear image of the car. You can see every detail, from the gleaming headlights to the tread marks on its tires. But while you've frozen the car in time, the picture doesn't tell you how fast it was moving. Now, what if you change your settings and use a slow shutter speed? This time the car appears blurred in the photo. You can clearly see that it was racing, the streaks of motion showing its speed. But in this blur, you can no longer pinpoint its exact location. It's as if the car is smeared across the image, caught somewhere between where it started and where it's headed. Heisenberg found something similar in the quantum world. He showed that you can't know everything about a particle at once. If you pin down its position exactly, you lose track of its speed. If you measure its speed, its position becomes fuzzy. It's not because our tools aren't good enough. It's because nature itself is uncertain, built on a kind of cosmic guesswork. This was mind-bending. In the everyday world, we expect certainty. Drop a ball, and it falls, kick a stone, and it moves. But in the quantum world, nothing is certain. Particles are like ghosts, flickering between possibilities, never fully one thing or another. Heisenberg's idea was a bombshell, and it set the stage for an even stranger discovery about the vacuum. Here's where the story gets wild. Heisenberg's uncertainty principle doesn't just apply to position and speed, it also applies to energy and time. Imagine you're looking at a tiny patch of empty space, like the inside of our box. You might think it has no energy, just pure nothingness. But Heisenberg showed that if you zoom in on a very short moment of time, the energy in that space becomes uncertain. It's like the universe is playing a cosmic loan game. It can borrow energy from nowhere, as long as it pays it back quickly. And with that borrowed energy, something astonishing can happen. Particles, real physical particles, can pop into existence right out of the vacuum, then vanish just as fast. It's as if the void is bubbling, fizzing with tiny bursts of creation and destruction. These fleeting specks are called virtual particles, and they're not just a theory, they're a fundamental part of how the universe works. This idea was so bizarre that even Heisenberg struggled to explain it. But another mind, one of the strangest and most brilliant in science, took it further. His name was Paul Dirac, a British physicist who was as quiet as he was profound. Dirac was an odd figure, a man of few words who thought in pictures and equations. Growing up in Bristol, he'd been a shy boy, finding solace in math and technical drawing. Those skills shaped his mind, teaching him to see the world in geometric patterns like an artist sketching the invisible. By the 1920s, Dirac was at Cambridge, wrestling with a problem that had stumped the best physicists. There were two great theories of the time: Einstein's special relativity, which described the universe at high speeds, and quantum mechanics, which ruled the subatomic world. The trouble was, they didn't play nice together. When you tried to describe an electron, a tiny particle zipping around an atom, using both theories, the math fell apart. Dirac wasn't deterred. He dove into the equations, his mind weaving a tapestry of numbers and symbols. In 1928, he emerged with something extraordinary, a single equation that married quantum mechanics and relativity. It was beautiful, a masterpiece of simplicity and power, like a poem carved in mathematics. His equation described the electron perfectly, capturing its behavior in ways no one had before. But there was a catch, a twist that even Dirac hadn't expected. The equation didn't just describe one kind of electron, it described two. Alongside the familiar electron, with its negative charge, there was another particle, a mirror image with a positive charge. Dirac called it an anti-electron, but we know it now as a positron, the first hint of antimatter. Antimatter sounds like science fiction, but it's real. Every particle has an opposite, a twin with contrary properties. When a particle meets its antiparticle, they annihilate each other, turning into pure energy in a flash. Dirac's equation suggested that the vacuum wasn't just bubbling with virtual particles, it was a dance of matter and antimatter, pairs of electrons and positrons popping into existence and vanishing before anyone could notice. This was a new picture of nothingness, not a dead, empty void, but a lively, seething realm where creation and destruction played out in the blink of an eye. The vacuum is a stage, and the quantum world is its wild, unpredictable show. But could this be proven? Ideas are one thing, evidence is another. In the 1940s, an American physicist named Willis Lamb set out to test the quantum void. Lamb was a master of precision, a scientist who could measure the unmeasurable. He knew that electrons in atoms orbit at specific energy levels, like cars on a racetrack. But if the vacuum was full of virtual particles, those particles should nudge the electrons, making their orbits wobble ever so slightly. It's like a car hitting tiny bumps on the road, shifting its path just a fraction. Lamb designed an experiment to detect this wobble, using microwaves to probe the energy of electrons in a vacuum chamber. The measurements were so delicate that a single mistake could ruin everything. But when Lamb ran the experiment, the results were clear. The electrons were wobbling exactly as the quantum theory predicted. The vacuum wasn't empty, it was alive, its invisible fluctuations leaving a mark on the atoms themselves. This discovery, known as the Lamb shift, was a triumph. It showed that the quantum void wasn't just a theory, it was real, measurable, a part of the universe we could touch. Scientists today still study these fluctuations, using lasers and high-tech chambers to catch the vacuum in the act. Quantum mechanics, for all its weirdness, is the most accurate description of nature we have. But the story doesn't end here. The quantum void isn't just a curiosity. It's a key to something far bigger. Those fleeting particles, those bursts of energy, hold a clue to the birth of the universe itself. What if the cosmos, with its galaxies and stars, sprang from the same nothingness we've been chasing? That's a question for our next chapter. For now, let's pause with the vacuum's hum, its secret life revealed. Because if nothing is alive, what does it mean for everything? We've journeyed from the tiniest specks of nothingness to the edges of the infinite, unraveling the secrets of the void and the stars. In our last chapter, we discovered the quantum void, a seething realm where particles and antiparticles flicker in and out of existence, defying our idea of emptiness. Heisenberg and Dirac showed us that the vacuum is alive, a bubbling cauldron of possibility. But what if this restless nothingness isn't just a curiosity? What if it's the seed of everything we see? The galaxies, the stars, the planets, even us? This is the story of how the quantum world shaped the cosmos, weaving a tapestry of light and matter across billions of years. It's a tale of daring discoveries, of telescopes that pierced the heavens and equations that rewrote reality. It begins with a single star, blinking in a distant nebula, and ends with the blueprint of the universe itself. Let's step into the early 20th century, a time when the universe was still a mystery wrapped in a puzzle. Thomas Digges had imagined an infinite cosmos, and the Herschels had mapped our Milky Way. But no one knew how big the universe truly was. Was our galaxy the whole show, or were there others out there, floating in the vast void? The answer lay hidden in those strange cloudy patches in the sky called nebulae. Some thought they were gas clouds within the Milky Way. Others dared to dream they were entire galaxies as vast as our own. They felt so far away, so untouchable. But in the 1920s, a quiet genius was about to bring them closer, unlocking the true scale of everything. Her name was Henrietta Leavitt, and she worked at the Harvard College Observatory, a place buzzing with starlight and ambition. Leavitt wasn't allowed to touch the telescopes, those were reserved for the men, but she had something better, a brilliant mind and an eye for detail. Her job was to study photographic plates, glass sheets capturing the night sky, and catalogue the stars. It was meticulous work, like finding needles in a haystack of light. But Leavitt loved it. She'd mark tiny specks, noting their brightness, their patterns, searching for clues. One day, she noticed something special about a group of stars called Cepheid variables. These stars weren't steady, they pulsed, brightening and dimming like cosmic heartbeats. Leavitt realized that the speed of their pulsing was linked to their true brightness. The faster they blinked, the brighter they were. This was a game-changer. Imagine two Cepheid stars pulsing at the same rate. They should be equally bright, right? But if one looks dimmer, it must be farther away. By comparing their apparent brightness, Leavitt could calculate their distance like a cosmic ruler stretching across the sky. It was a simple idea, but it was revolutionary. For the first time, astronomers had a way to measure distances far beyond the Milky Way, to probe the nebulae that had puzzled the Herschels. Leavitt's discovery was a key, but she couldn't turn it herself. Forbidden from using telescopes, she passed the torch to others. And one man, a larger-than-life astronomer named Edwin Hubble, was ready to run with it. Hubble was ambitious, driven to make his mark on the cosmos. In 1923, he turned the telescope toward a nebula called Andromeda, a faint spiral that had intrigued astronomers for years. Night after night, he studied its light, searching for Cephid stars. Using Leavitt's method, Hubble calculated its distance. The result was staggering. Andromeda was over 2 million light-years away, far beyond the Milky Way's edges. It wasn't a cloud, it was a galaxy, a vast island of stars as grand as our own. This was a bombshell. The universe wasn't just the Milky Way, it was a multitude, billions of galaxies scattered through an unimaginable expanse. Hubble's discovery, built on Leavitt's quiet brilliance, showed us that the cosmos was vaster than Diggs's wildest dreams. But Hubble didn't stop there. He kept observing, studying galaxy after galaxy, and noticed something even stranger. Their light was stretched, shifted toward the red end of the spectrum. This redshift meant they were moving away from us, and the farther the galaxy, the faster it fled. It was as if the universe itself was stretching, growing bigger every second. Hubble's observations were proof that the universe wasn't static. It was expanding, a living, breathing entity. This idea of an expanding universe wasn't new, but it was controversial. A decade earlier, Albert Einstein had wrestled with the same possibility. Einstein's general theory of relativity, a masterpiece of mathematics, described how space and time bend around mass, creating gravity. But when he applied his equations to the entire universe, they suggested something wild. The cosmos wasn't fixed. It could expand or contract, like a fabric stretching or shrinking. Einstein couldn't believe it. A dynamic universe seemed too strange, so he added a fudge factor, a cosmological constant, to keep it steady. But Hubble's data proved Einstein wrong. When Einstein visited Mount Wilson, he saw the redshift for himself and called his constant his biggest blunder. The universe was expanding, and that meant it had a history, a beginning. If the universe is growing, rewind the clock far enough, and every galaxy, every star, must have been squeezed into a single tiny point. This was the Big Bang, a moment of creation 13.7 billion years ago when the cosmos burst into being. The idea was radical, almost unthinkable. A universe born from nothing? It sounded like myth, not science. Many scientists resisted it, but one piece of evidence could change their minds. A faint glow, a whisper of light from the Big Bang itself. In 1965, two astronomers, Arno Penzias and Robert Wilson, found it by accident. They were testing a radio telescope in New Jersey, picking up a strange hiss no matter where they pointed it. That hiss wasn't noise. It was the cosmic microwave background, the stretched-out remnant of the Big Bang's first light. Penzias and Wilson weren't looking for the universe's birth. They stumbled onto it like finding a treasure in the attic. That glow, still detectable today, is proof that our universe began in a flash of heat and light. But the Big Bang wasn't just an explosion, it was a quantum event, tied to the restless void we explored with Dirac and Heisenberg. In its earliest moments, the universe was smaller than an atom, governed by quantum rules. The vacuum's fluctuations, those fleeting bursts of energy, left tiny ripples in the newborn cosmos. As the universe expanded, those ripples grew, becoming seeds for the galaxies we see today. To prove this, scientists launched a satellite called WMAP in 2001. It mapped the cosmic microwave background in exquisite detail, revealing faint variations in temperature, scars of the quantum void. Those specks were the blueprints of the universe, proof that the quantum fluctuations of nothingness shaped the cosmic web, the vast network of galaxies and voids that defines everything. The cosmic web is a stunning picture of the universe's structure. Imagine filaments of galaxies like glowing threads, linking clusters of stars across billions of light-years. Between them lie vast voids, empty spaces where the quantum seeds never grew. This web, born from the Big Bang's quantum ripples, shows us that nothing and everything are intertwined. The galaxies we see, the stars that light our nights, even the atoms in our bodies, all trace back to the vacuum's restless dance. It's a humbling thought. Science has woven this story from Leavitt's pulsing stars to Hubble's red-shifted galaxies to WMAP's ancient light, showing us that the universe is a quantum creation vast yet intimate. But this story isn't finished. The cosmic web is still growing, still changing, and Hubble's expanding universe holds a secret that no one saw coming. In 1998, astronomers studying distant supernovae made a shocking discovery. The universe isn't just expanding, it's speeding up, driven by a mysterious force we call dark energy. This force, invisible and unknown, is pushing galaxies apart faster and faster. What does it mean for the future? Will the cosmic web unravel, leaving only darkness? That's a question for our next chapter. For now, let's linger with the cosmic web, its thread spun from the quantum void. Because if nothingness shaped the universe, what will it do next? We've travelled from the whispering void to the sprawling cosmic web, tracing the story of nothing and everything. In our last chapter, we saw how the quantum fluctuations of the vacuum seeded the universe, birthing galaxies from a fiery Big Bang. Henrietta Leavitt's pulsing stars, Edwin Hubble's red-shifted galaxies, and the cosmic microwave background revealed a universe that's not just vast but alive, expanding from a single point 13.7 billion years ago. Yet as we stand beneath this glittering tapestry of stars, a shadow looms, a mystery that challenges everything we've learned. The universe isn't just growing, it's accelerating, racing apart faster than we ever expected. What's driving this cosmic sprint? And what does it mean for the future of everything? This is the story of the dark unknown, a force so strange it defies our understanding, yet holds the fate of the cosmos in its grasp. It begins with a flicker of light from a dying star, a clue to the universe's deepest secret. Let's step into the 1990s, a time when the world felt electric with possibility. The internet was sparking to life, music was blasting from Walkmans, and astronomy was entering a golden age. Telescopes were sharper, computers were faster, and scientists were hungry to answer big questions. One of those questions was about the universe's fate. Edwin Hubble had shown that the cosmos was expanding, galaxies drifting apart like leaves on a stream. But what would happen next? Would the expansion slow down, pulled back by the gravity of stars and planets until the universe collapsed in a big crunch? Or would it keep stretching forever, fading into a cold, dark void? Astronomers had been debating this for decades, and they needed data, hard, clear evidence to settle it. The key to this puzzle lay in supernovae, stars that explode in a blaze of glory. There's a special kind called Type Ia supernovae that always explode with the same brightness, like cosmic light bulbs with a fixed wattage. If you know how bright they should be, you can figure out how far away they are by how dim they look from Earth. It's the same trick Henrietta Leavitt used with defied stars, but supernovae are visible across billions of light years, far beyond our galaxy. Two teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, set out to use these supernovae to measure the universe's expansion. Their plan was simple: find as many Type Ia supernovae as possible, measure their distances, and check their redshift to see how fast they're moving away. By comparing nearby supernovae to distant ones, they could tell if the expansion was slowing down or speeding up. They'd work through the night, sipping coffee, waiting for data to stream in from telescopes in Chile, Hawaii, or space itself. They found dozens of supernovae, each a beacon from the distant past, their light travelling for billions of years to reach us. By 1998, both teams had enough data to draw a conclusion. They expected to see that the universe's expansion was slowing, that gravity was winning the tug-of-war. But when they crunched the numbers, the results were staggering. The distant supernovae were dimmer than they should have been, meaning they were farther away than expected. The universe wasn't slowing down, it was speeding up, accelerating like a car with the pedal to the floor. This was a shock, a cosmic plot twist no one saw coming. The astronomers double-checked their work, thinking there must be a mistake. Dust in space, faulty measurements, something had to explain it. But the data held firm. The universe was expanding faster now than it had billions of years ago. Something was pushing galaxies apart, counteracting gravity's pull with a force no one understood. The teams called it dark energy, a name that was more placeholder than explanation. It wasn't a substance you could see or touch. It was a mysterious energy woven into the fabric of space itself. Dark energy was a ghost, invisible yet powerful, driving the universe toward an unknown future. To grasp how strange this is, let's think about gravity for a moment. Gravity is the force that holds us together, planets orbiting stars, galaxies clustering in the cosmic web. It's like a cosmic glue, pulling matter closer. Dark energy is the opposite, a repulsive force that stretches space apart. Einstein had stumbled onto something like this decades earlier. His cosmological constant, the fudge factor he added to keep the universe static, could act as a kind of anti-gravity if given the right value. When the supernova results came in, scientists dusted off Einstein's idea, wondering if dark energy was the cosmological constant reborn. But what was it? Where did it come from? And why was it strong enough to overpower gravity now when it hadn't before? These questions sent physicists scrambling, and one place they looked was the quantum void we met in our last chapter. The quantum void, with its bubbling virtual particles, is more than just a lively emptiness. It's a source of energy. Those fleeting bursts of particles and antiparticles carry a tiny bit of power, a hum that fills every corner of space. Physicists call this vacuum energy, and it's a prime suspect for dark energy. The idea is tantalizing. What if the same quantum fluctuations that seeded galaxies are now pushing them apart? It's like the vacuum is a cosmic engine, creating the universe and driving its expansion. But there's a problem, and it's a big one. When scientists calculated the vacuum's energy using quantum theory, the numbers were absurdly large, trillions of times stronger than what dark energy seems to be. It's like expecting a whisper and getting a supernova. This mismatch, called the cosmological constant problem, is one of the biggest headaches in physics. If the vacuum's energy is so powerful, Why isn't the universe expanding at breakneck speed? Or if dark energy is something else, what could it be? Let's meet a physicist who wrestled with this puzzle. Lisa Randall, a Harvard theorist with a knack for tackling the impossible. In the early 2000s, Randall was exploring the idea of extra dimensions, hidden realms of space beyond the three we know. It sounds like science fiction, but it's rooted in string theory, a framework that tries to unite quantum mechanics and gravity. Randall wondered if dark energy could be tied to these extra dimensions, a kind of leakage from a hidden world. Her ideas were bold, speculative, but they sparked a new way of thinking. Maybe dark energy isn't just a property of our universe, maybe it's a signal from somewhere else, a place we can't yet see. Her work, like so much in cosmology, reminds us that the universe is full of surprises, waiting for the right mind to uncover them. Meanwhile, astronomers were gathering more clues. In 2003, the Sloan Digital Sky Survey began mapping the cosmic web in 3D, charting galaxies across billions of light years. The survey showed that dark energy isn't just speeding up the universe, it's shaping its structure, stretching the filaments and voids of the cosmic web. Then came the Planck satellite in 2013, which refined our map of the cosmic microwave background, the Big Bang's afterglow. Planck's data pegged dark energy as 68% of the universe's total energy, with normal matter, stars, planets, us, making up just 5%. The rest is dark matter, a mysterious substance that binds galaxies together. We're just a tiny fraction of the cosmos, dwarfed by forces we barely understand. Dark energy is the dominant player, and it's been hiding in plain sight all along. But what does dark energy mean for the future? If it keeps pushing, the universe will expand forever, growing colder and darker as galaxies drift beyond reach. Stars will burn out, black holes will evaporate, and the cosmic web will fray into nothingness, a fate called the Big Freeze. It's a haunting thought. Yet some scientists think dark energy could change, growing weaker or stronger, leading to different endings. If it reverses, the universe could collapse in a big crunch. If it surges, space could tear apart in a big rip. These possibilities are speculative, but they keep cosmologists up at night, dreaming of new experiments to pin down dark energy's nature. Today, projects like the Dark Energy Survey and the upcoming Vera C. Rubin Observatory are hunting for answers, scanning the sky for supernovae, galaxy clusters and gravitational lensing, light bent by massive objects. These clues could reveal whether dark energy is the vacuum's hum, a cosmic constant, or something entirely new. Every discovery brings us closer, but the mystery remains. Dark energy is the dark unknown, a force that shapes our past and future, yet slips through our fingers. Here we pause, at the shimmering edge of nothing and everything, where the universe unveils its grand paradox. From Aristotle's ancient dread of the void to Pascal's daring climb into thinning air. From Leavitt's pulsing stars to Hubble's galaxies fleeing into the infinite, we've traced a tapestry woven of absence and abundance. The quantum void hums with secrets, birthing particles that seed the cosmic web. While dark energy, the universe's silent puppeteer, pulls the strings of an ever-faster dance. What lies ahead, eternal frost, a cosmic collapse, or a mystery yet unnamed? That's for us to chase, with the same restless wonder that turns straws into revelations and starlight into maps. As Stephen Hawking once whispered to the stars, however bad life may seem, there is always something you can do and succeed at. While there's life, there is hope. So let's keep looking up, into the nothing that holds everything, and dream.